So before I talk about CUDA, I want to talk about something called GPGPU, just so that for some of you who know some history, you probably know enough of the history to hurt yourself. So, sometimes it's better either not to know anything or know something really well. Because if you know a little bit of something, sometimes it's just, very harmful. And this is one of the situations. A GPGPU, or general purpose GPU, is essentially to use GPUs for applications other than 3D graphics. And basically the idea is to use GPU to execute the part of the application that's on critical path, and use the GPU computing power and resources to speed up that critical path. And basically, people want to use GPU for the data parallel portions of these applications. Okay. What is the data parallelism? Well, the data parallelism is a property of a program where you have a large data structure, such as a big array. And you can do operations on different parts of the data structure in parallel. Okay, so that's just a generic meaning of data parallelism here. And so mostly the kind of application that people use these GPUs are for is large data arrays and streaming throughput. That is, oftentimes you also have a situation where you have a lot of data coming to you, okay, coming through this machine. And the calculation that can be done on the data is actually independent from data portion to data portion. So that's also where you can do a lot of throughput-oriented data parallel processing. And mostly they are done with very fine-grained, what we call the single instruction multiple data processing. That is, you use a single instruction and you execute that instruction on a large number of data. Okay? And this is a very common mode of parallel processing in practice, like vector processing and so on, that many of you know about. And so the idea is that the processor only needs to get one instruction, and then it applies the instruction to many data. So applications, you can go to gpgpu.org, and oftentimes you will see things like games and physical effects of games, and physical modeling, computational engineering, matrix algebra, convolution, correlation, sorting. So this thing has been around for more than 6-7 years. Okay, it's a fairly big kind of activity that the GPU vendors push. The problem with this, what we call the previous GPU, is the constraints that gets imposed on the programmers. Basically, all these programming models are built on what we call the graphics APIs. Okay, so for those of you who are familiar with graphics, there's something called OpenGL, and there's some kind of direct, 3D DirectX, kind of API. All these APIs, or application programming interfaces, are essentially functions that the programmers can call in order to make things happen on these GPUs. There's no other way you can use the GPU. You have to use one of those functions to get to this GPU hardware. So if you need to calculate something like, let's say, a weather forecast, you need to figure out some kind of computation. You scratch your head and say, here's my program here, and how do I make this program into a sequence of calls to taking triangles, drawing triangles, rotating triangles? That's essentially what it is. Okay? And so but there's one very fundamental issue, which is what we call the data marshalling process. Which means whenever you call these things, you have to put all the data into the exact format that those APIs accept. That is the function call parameters. You need to fit into those function call parameters. So you need to somehow copy all your data into a form that the functions expect. And then you do some computation, and in the end, the function can return one value. Okay? If you need to return a lot of values, you're out of luck. You call the function many times. right? So that's how the GPGPU computation was done, and it turned out it's so difficult that very few people actually use it. There are only, maybe a few hundred people in the world who can actually use it for, for something useful. And that has been a very, very difficult process. Therefore, what we're teaching this semester has very little to do with that whole interface. What you're going to be doing in order to use the GPU is not to do those function calls. Okay, those function calls are just way too awkward for most of the computation that you're going to try to do. So what NVIDIA did late last year was when they designed the G80 chip, they actually put in a small piece of hardware, additional hardware that they never had on those chips. And that piece of hardware essentially is a general purpose programming interface that accepts more regular CPU types of instructions, okay, from the users. So that you can fetch instructions, you can do these more traditional processing functionalities. And whenever the user runs the GPU in CUDA mode, that piece of hardware takes over as the control mechanism, rather than the original GPU control mechanism. Okay, so this is what we call the dual personality. You set the mode, then one of the controllers take place. The acronym has been, the same, but the spelling has been changed several times. So the current spelling, the current, sort of representation is Compute Unified Device Architecture. And David Kirk is going to come in next week, so you can ask him exactly why, they came up with this, acronym. The general purpose programming model essentially, it's a general purpose programming model in the sense that users will kick off batches of threads on the GPU. And we're going to show you exactly how you do it by the end of the lecture. Okay? And the GPU is really a dedicated, super-threaded, massively data parallel coprocessor. Okay? And that has nothing to do with graphics, except in some cases you will see some tidbits of traces of being a graphics processor, because you will see something called texture memory. And we're going to get to that. There's a driver, software driver, which is totally different from the graphics software driver that allows you to use this device as a compute device. It's a standalone driver. It's optimized for computation, so you're not seeing any of those graphics-oriented, frame buffer, like all those things in the traditional graphics driver. The interface design is for compute, so all the APIs are going to be more programming rather than graphics that you're going to see them today. But you can do data sharing with OpenGL buffer objects, and what that means is that you can actually run the GPU in alternative modes. Okay? You can run the GPU as compute mode, compute all the information, and then put that into a sharing mode. And then you invoke the graphics mode that you can render your computation result in place in the GPU card, so that you don't have to move data back and forth between the CPU and the GPU. Okay? And that actually turned out to be a very useful feature for most of the scientific computing community, where you want to be able to do high performance compute and render. You don't want to waste your time shuttling data back and forth. You have guaranteed maximum download and read-back speeds, because you no longer have to fit into some kind of GPU operation, and it's explicit GPU memory management, and you're going to see those calls. So before we go into the abstract programming model, for those of you who would like to sort of see some of these things in more concrete form, this is a kind of example of physical reality behind CUDA. Okay, so this is one of the recent Intel PC architectures, and let me just quickly go over this. This is essentially the memory channel hub, which is a chipset. For those of you who are hardware-oriented, it's one of those chipsets that controls the connection between the CPU, the memory, and the rest of the system. Okay, and this chipset essentially is a hub of what we call the PCI Express interface. It's a PCI hub, okay? And I'm not going to give that lecture until later. It used to be lecture 4, but I'm going to go over that later. So if it doesn't make a whole lot of sense to you yet, don't worry about it. But for those of you who use PCs, you know that in the back of the box, you have these PCI slots, right? And those are, that's exactly the same PCI we're talking about here. So the graphics GPU is actually hooked into the hub through what we call the X16 PCI interface. And that provides you 8 gigabytes per second bandwidth, 4 gigabytes each way, simultaneous, okay, to the CPU. Unfortunately, the Intel CPUs don't have exactly 8 gigabytes per second, so you won't be able to take full advantage of that bandwidth, but the next generation Intel CPUs will. The CPU will actually go through the same hub to the memory, and the GPU could access the global memory also through the same hub. What we're talking about in CUDA, when we talk about host, it refers to the CPU. Okay? And whenever we talk about the device, we refer to the GPU. They are connected through a bus that is fairly fast, but not of infinite speed. So you're going to see some data transfers between the two, which reflects the reality that you need to actually move data back and forth between the system DRAM and the GPU. Okay? So that's essentially the reality behind a lot of these function calls. So what do people use today when they use CUDA? Well, it turned out that there is a whole product line of things that NVIDIA has that essentially provide a kind of a scalable line of compute products. You can have the GeForce 8800 GTX, which is going to be where you're going to be doing most of your early part of the hardware work, for this class. And we built a cluster of those machines. Each one has one of these, and that will be, where you're going to be doing most of your initial projects. And then you will have, there's a Tesla, what they call the half 3U box. And these are actually, 2 of them can fit into a 3U server rack. And you can build servers out of them. Okay? And we're actually going to have a bunch of those in September. So, we're going to begin to see some even higher performance configurations in the middle of the semester. And then you have ultimately what they call the 1U Tesla form factor. Oh, by the way, the Tesla box, the half 3U box, has 2 GPUs in each one. Okay, and then eventually you'll have a 1U box, 1U unit that will actually have 4 GPU in each unit, and that's going to be the standard server architecture in the future. And eventually we'll move into this kind of architecture. And this thing is going to give you about 2 teraflops per unit. Okay, and 2 teraflops used to be incredibly expensive just a few years back. Okay, you need to spend probably a couple $1 million to get the 2 teraflops just a few years back. So this is a incredible amount of computing power for several $1,000s. What we showed last time was some of the previous students actually had about 50 to 200 gigaflops of performance out of their applications. And the GPU parallelism is doubling every year, so the next few generations, you will see products into these forms, but the GPU chips will increase their parallelism by 2 times about every year. So when you write these programs, you also need to remember, it's not just for this particular GPU chip, but for the future generations, you should be able to take advantage of the doubling of parallelism every year or so. And that has some ramifications about how you write these applications. The programs are really written in C with CUDA tools, and it's in a form called SPMD, Single Program Multiple Data. And this is a form that a lot of the scientific computing people have been using. Essentially, it's a data parallelism program. So you only run one copy of the program. So the program will generate many threads. Each thread will operate on a piece of data. The difference between SIMD and SPMD is that even though you have the same program as SPMD, each thread could follow a different control path. So you could have one thread doing the if part and another thread following the else part of a if then else, and it will work just fine. Okay? And we're going to go into a little bit more intricacy later on. CUDA programs are essentially extended C programs. And what are the extensions? The extensions are listed on the left-hand side. This is the first one is declarations. You will have a few declarations, what we call deco specs, that will mark the functions as global device shared, or in some data structure to be global device shared. Okay? So, and local and constant. So, for example, we can say that this particular data should be a device data structure. And what that tells the compiler is that allocate this piece of data in the GPU memory rather than the CPU memory. Okay? And you can mark each function as global device or global or device. So in this particular case, the convolution function is marked as global. And we're going to come back to the reason why there's a very specific meaning about global. A function can also be device, or it could be host. Whenever you don't say anything about the function, it's actually a host function. The default is it's going to be on the CPU. But whenever you say a function is device, then that function will be the binary code for that function will be generated for the GPU, so that you can execute that function on the GPU. Remember, the GPU is a different hardware instruction set than the host, okay, the CPU. So that's the reason why you have these declarations. You have keywords. The keywords are often used to access special variables that reflect hardware features. For example, you can have a keyword access to thread index. Whenever you use an array with the mentioning of thread index, the thread index is not a real variable. It's actually a hardware register. And that hardware register gives the particular thread being executed now access to its own ID. Okay. So the thread is a generic piece of code, but as long as you give it a unique ID, it will do unique things. So this is how threads distinguish themselves from each other. So these keywords allow the threads to access different parts of the data structure according to its own identity. They're intrinsics. Intrinsics is used to refer to things in general that appear to be function calls, but they get mapped into hardware features. In digital signal processing, a lot of these DSP processors have intrinsic functions. And when you call these functions, they get translated into special DSP instructions, such as saturating arithmetic addition. That's a DSP intrinsic function. If it doesn't make sense to you, don't panic, because this is for the benefit of people who come from DSP domain, and I'm not going to test you on any of that stuff. So sync threads in this particular programming model is a function call, appears to be a function call, but it actually gets mapped into a hardware synchronization instruction. And that hardware synchronization instruction is a barrier synchronization, and I'll explain more details later. There's also runtime API calls. application programming interface calls. There's a bunch of real functions that the programming model supplies to you that help you to do things more easily. And these things include memory management. Right? In C programming, you will have malloc. In CUDA, you will have CUDA malloc. So this gives you a bunch of memory. Could be either in CPU or GPU according to your specification. And this particular case, CUDA malloc actually only allocates memory in the GPU DRAM. Okay? And then you have what we call the function launch. You call one of your functions, it has to be a global function, and this function you will supply something here, then I will tell you later, which means you specify the number of blocks and number of threads in each block that you will generate. So the hardware actually will take over and generate all those threads. The threads are generated by hardware. The function call just triggers the hardware to generate those threads. In this particular case, we'll generate 100 blocks of threads, and each block has 10 threads in it. So we're generating a total of 1,000 threads with this function call. The function call is a very, very short function call, and it leads right into hardware in GPU, and it will generate all those 1,000 threads in just a few clock cycles, a very small number of clock cycles. Okay? So these are the extensions, all the extensions that you need to learn about CUDA. Otherwise, it's C. So if you have some C programming background, you'll be fine. And we'll just tell you the details about how these extensions work. Behind the scenes, what happens is that you will be writing an integrated source. So you will be writing essentially a C program with these extensions, right? And that's one source program. But remember those deco specs. Those deco specs helps the compiler to separate out the code that it needs to generate code for the CPU and it needs to generate code for the GPU. So that is based on what they call the CUDA ACC. At that point, it takes all these keywords and so on and split up the code into two paths. One path goes down to the GPU path that will generate assembly code and object code, and eventually it will become executable binary for the GPU. Okay? And the other one, you will actually generate CPU host code for Linux that will be GCC, and will generate the appropriate code for the CPU. And in the end, the runtime will just glue the two together so that the CPU can invoke the GPU code. The GPU code can actually go back to the CPU code. You go back and forth. Okay? So we're going to talk about some basic concepts and data types. We're going to talk about the application programming interface. And we'll talk about the basic ones. We'll have a simple example to illustrate the basic concepts and functionalities, and we'll talk about some performance features later, not today. Okay, we're not going to be talking about anything high performance today. In fact, by the end of the lecture, I'm going to talk about one piece of code that will be very low performance on that chip. Okay, remember, parallel programming is very easy if you don't care about performance. I'll prove it in an hour, right? Okay, now, so the CUDA programming model is, again, essentially a CPU plus a highly multi-threaded coprocessor. And the GPU is viewed as a compute device. I already went over that, right? And it is a coprocessor to the CPU, and CPU is called a host. The GPU has its own DRAM. The board that you're using this semester has 768 megabytes of DRAM on the GPU board. Okay, it's quite substantial. It's not incredibly big, but 768 megabytes is quite good for a lot of the computation you're going to do. And it runs many threads in parallel. In fact, it can run up to 12,288 threads all active at the same time on that chip. Okay, 12,000, more than 12,000 threads physically. Okay. Now, the data parallel portions of an application are executed on the device as kernels, and you're going to hear this name multiple times. Each time you want to do something, you call a kernel. So the model is fairly simple. And I actually have a slide, so I'll wait until that slide is the next one. There are two main differences between CPU and GPU that you always should keep in mind. It'll always help you to think through these things. One is the GPU threads are extremely lightweight. Creating 10,000 threads on a GPU takes only a few cycles. Less than 10. Okay, you can count those cycles with the fingers of you with both hands. Probably less than 5. So there's very little creation overhead. You should not be afraid of creating threads on this machine. Whereas if you use P threads in Unix, you will know that these things come at a real cost. Okay. The second one is GPU actually needs thousands of threads for its full efficiency. Most of the applications that turn out to be very high performance usually have about 5,000 to 8,000 threads all running at the same time. That's about the scale that you need. So if your advisor says, since you took 498, you should write a GPU code to speed up my 4x4 matrix multiplication, you would tell your advisor very politely that it doesn't work. You don't understand, because the 4x4 matrix multiplication will not generate thousands of threads. Okay? So that's something that you will need to always keep in mind. Yes?
When this thing's operating as a GPU, does it automatically assign 12,000 threads?
Yeah, that's all under the API. So when you give, let's say, a list of triangles to render, and automatically the API will generate all the thousands of threads to do those.
So if you're using GPU, then you don't have to worry about the threads. Is that an advantage?
Correct. It is potentially an advantage, but the disadvantage of having to fit into the rendering model usually takes away. So that's why they moved to this model, because most of the programmers ended up saying that let me handle the threads. But the key issue is not necessarily handling the threads. It's really just being able to handle the threads in such a way that it's scalable and you can get performance out of it. And that's the tough part. Handling threads generically is actually quite easy. Okay. Unfortunately, if you want to fit into the API model, you'll need to go through the same thing. You'll even have to second guess what the threads are in order to get performance. Okay, now, so this is the slide I was talking about here. When you execute a piece of host program, let's say you have an application, and you execute the application, and you will hit phases of the application where you will have lots and lots of data parallelism. So let's say you're doing a medical imaging, reconstruction, and every once in a while you will see a big FFT operation or big non-uniform Fourier transform operation, and those things will be candidates for a kernel because they will need to operate on a fairly large image. Okay, so that will be one kernel call, and then later on, so after you finish, you go back, there will be something else that has a lot of data parallelism, and then you do another kernel call, and each kernel call is a global function definition. Okay. So kernel 1, when you execute kernel 1, it will go and generate a huge number of threads. And the threads are organized in the following way. All the threads generated for the kernel will be organized into a grid. Okay, this is a proper name in the model. So it's a grid of threads. The grid of threads will contain multiple blocks of threads. Okay, and when you have multiple blocks of threads, each block can also contain up to 3 dimensions of threads. So the blocks are organized into 2 dimensions, and within the block, threads can be organized into up to 3 dimensions. You can also organize them into 2 dimensions or 1 dimension according to your needs. Okay? So that's portrayed here. This is an example where you have a 2-dimensional thread in a block. Now, a thread block has the feature where all the threads in the block can synchronize with each other. You can use sync threads to synchronize with all the other threads in the same block, but not across blocks. Okay, this is one of the limitations that you're going to run into. You can only synchronize between threads using sync threads, intrinsic. Remember that intrinsic I just talked about? Okay? And also, there is a very, very efficient way for these threads in a block to share data. You can access a shared memory in a very small number of cycles. I'm talking about probably close to 1 clock cycle. You can read, write a shared memory, okay, that's shared among all the threads in a block. But you cannot efficiently share data across blocks. Okay? Now, there are 2 threads from different blocks cannot cooperate. So the only way, if you really want to synchronize between 2 thread blocks, the only way to do it at this point is to terminate the kernel. Okay? Essentially terminate all the threads that you currently have. You write everything into the global memory, you terminate all the threads, and then you restart the kernel. At that point, you can read all the data back, and they will be fully synchronized. This turned out to be an expensive process for some applications last semester. Okay, we have some students running into that problem. And that actually is being fixed, but it's probably not going to be in time for this semester. So block and thread IDs are accessed through the keyword. Remember, there was a keyword, thread index, right, and block index. Those are the 2 keywords for you to access your ID within the organization. So all the threads will know exactly where it is in terms of the organization, okay, through those 2 keywords. And it simplifies memory addressing. And we're going to show you with a very simple piece of code, each thread can actually go to exactly where it's supposed to access in the memory, because you can use the thread ID to help generate the addresses. Whereas in the previous API-based interface, you cannot do this. Okay, so that's another reason why those API interfaces are extremely hard to use. Yes?
So what's the benefit of having 1D, 2D, and 3D? Is it just a better way to think about it, or is there any actual benefit?
Yes. Wonderful. It turns out that these are conveniences. Whenever you use dense data structure to model 2-dimensional or 3-dimensional flows. The real reason why they provided it is not because they want you to have the convenience. The real reason why they provided it is available to the GPU. It was designed for the GPU, the graphics part anyway. Those organizations make the 3D graphics very efficient. However, they also made it available through the CUDA interface just so that the dense data structure also gets some convenient usage. Okay. We're going to focus on the GPU. Okay, so we're going to shrink the host into a smaller box, right? But in reality, the host is probably this big and the GPU is probably this big, right? So it depends on where your focus is. So we're going to have the host at the corner, and we're going to go through some of the CUDA features, okay, that correspond to each part of the model. So this thing is something that you will find very convenient for you to reference as you write these programs. Okay, these are good mental reference points for you in the future. You will think about each thread block, okay, as an execution unit. These thread blocks will be run at the same time. Okay, logically, you can think about these thread blocks as a unit of threads that will always kind of execute together in an abstract way. And within the block, you will have all these threads. Each thread will have access to what we call the local memory. It's a per thread local memory. Okay? There's no sharing across threads. Whenever you put anything into local memory, it's only accessible by the thread. Only, not any other threads. You also have a bunch of registers. You probably noticed that I have not talked about registers in the C extension, right? I'm not talking about anything about registers. Registers are not explicit entities in this programming model. But the compiler maps variables into registers. Why do I even bother to talk about registers? Because in reality, these registers constrain the number of threads you can run on the hardware. So you need to actually understand that limitation at the time being. Okay? So I'm introducing that it's not a fundamental concept of CUDA programming model. It's something you need to understand in order to get performance. All the threads will have access to a piece of shared memory. Okay? They can read, they can write the shared memory, they can exchange data. In order to enforce proper producer-consumer relationship, you need to do various synchronization between writes and reads so that you can make sure all the writes are complete before you read. Okay? So that's one very important use of the sync thread. So I talk about registers, I talk about local memory, I talk about shared memory. And there is a global memory, which is located in the DRAM. Okay? And this global memory is accessible by all the thread blocks. Okay? So whenever you write into global memory, it becomes visible to all the other threads. But there's no convenient way for you to synchronize and make sure they see exactly the version that you want them to see. So the only way to really make sure of that is to terminate the current kernel and then restart the kernel. Okay? You also have read-only per-grid constant memory. This is for the CPU to initialize a bunch of read-only data that will be consumed by the GPU threads. Turns out that this constant memory can be extremely useful for you to hold read-only data structures that provide a value that will be used by a large number of threads. So whenever you have a data structure, for example, let's say if you have a particular variable, but the variable is actually read-only in the kernel, you can initialize the variable in the constant memory. And then the hardware actually has a very effective caching mechanism to hold that constant value across all the processing elements. And all the threads can simultaneously read that value and has very high efficiency access to that value. And that was very useful for some of the applications, especially the medical imaging applications. Now, there's also a read-only per-grid texture memory. And this texture memory has some unique properties that we're going to introduce later on. The host can read-write global, constant, and texture memories, but the GPU can only write into global, not to the constant memory. And texture memory is writable, but you need to go through some kind of API, I believe, right?
Basically, yeah.
Yeah, it's kind of painful. So basically, global memory goes here, constant memory goes here, and texture memory goes here. The hardware has caching mechanism for constant memory and texture memory. Okay, that's all you need to know for now. Okay.